Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to discuss about star-star connection diagram. In three-phase transformer, we are going to discuss about star-star connection diagram. Right? Let's see here. For example, these are the three phases of the primary winding. Three phases of the primary winding. And these are the three phases of my secondary winding. Three phases of my secondary winding. I said you already, the primary parameters are denotes with capital letters and secondary parameters are denotes with small letters. Of course, this is A2, A1, B1, B2, C1, C2. Of course, A1, A2, B1, B2, and C1, C2 like this. And here, always take the dot notations at the second terminals. And now, this should be a star connection and this should be a star connection. Star connection nothing but all the phases are tied up at one point is called neutral and remaining ends are free each other. Like that, I am taking here all the first terminals of my three phases are connected to neutral and all the first terminals of my three phases are connected to neutral. This is a star-star connection with additive manner. This is with additive manner. Right? Now let's draw the star, arbitrary star and arbitrary star for both. Here take, this is a neutral, this is a neutral. From the neutral, the vector A is for A2 and vector B is for B2 and vector C is for C2. Vector C is for C2. This is the arbitrary star. And for this also, this is in additive manner, right? For additive manner, vectors are in phase, are in parallel. So how? From here also, the small a should be here, and small b should be here, and small c should be here. All or should be in parallel. Of course, for example, this is my neutral. From the neutral, small a for A2 and small b for B2 and small c for C2. These are the arbitrary star. Right? Now superimpose these two on a clock. Superimpose these two on a clock. This is 12 o'clock and this is 6 o'clock. I said you the primary winding vector, is represents with capital letters, which is a minute's hand. This is my minute's hand is a upward direction. And here also the secondary, nothing but hour's hand also in upward direction. Both are in upward direction. Both are in phase to each other. Both are in phase to each other. So now tell me, here the primary is a star, represents with capital letter Y. And secondary is also star, represents with a small letter, small y. And the time is 12 o'clock. It represents what? It represents that 0 degrees displacement in between primary and secondary in star-star connection. For example, this is the first configuration. And let's change the configuration to get the 180 degrees. Let's change the secondary configuration. I'm going to change the secondary configuration. Now I'm not taking here neutral. I'm taking neutral. I'm taking neutral at this side. This side. This is my neutral. This is my neutral. Now tell me, this is the additive manner or subtractive manner? This is ultimately subtractive manner. Because see here opened, but here neutral is connected. This is ultimately subtractive manner. So for subtractive manner, the vector should be exactly 180 degrees. The secondary vector should be 180 degrees to the primary vector. So see here my capital A in upwards. So here our capital A should be downwards. Our small a should be downwards. Here my B is in this direction. So here B should be in this direction because 180 degrees. So it should be in this direction. This is my small b. Here my C is in this direction, but here in opposite direction, exactly in opposite. So this is my small c. This is my small c. Now tell me from the neutral, the small a, from the neutral small a for A1, small b for B1, and small c for C1. Small c for C1. These are the arbitrary star. Now represents that arbitrary star on the clock, superimpose that on the clock. Again, here the capital A or our minute's hand is in the same upward direction, but our hour's hand is in exactly downward direction. So from here, our capital A is upwards and small a is in downwards. Now tell me what is the angle? What is the angle between hour's hand and minute's hand? Hour's hand and minute's hand displaced by 180 degrees. Here the primary and secondary windings are displaced by 180 degrees phase difference. These two vectors are 180 degrees phase difference. So here primary is the star, secondary is also a star, but the time is 6 o'clock. 6 o'clock represents with 180 degrees phase difference. 6 o'clock represents that 180 degree phase difference. 180 degree phase difference. This is simply about the star-star connection. Again, you have a doubt. Sir, if we change the connection diagram of star, again you got two configurations. In that one is 0 degrees and other one is 180 degrees. Nothing but in star-star also, the phase shift between primary and the secondary is either 0 degrees or 180 degrees. Either 0 degrees or 180 degrees. This is for star-star connection diagram. In delta and star-star, the phase difference between primary and secondary vectors is either 0 or 180 degrees based on the connection diagrams. Right? Is it okay? Now let's see here. Now we completed the connection diagrams. Now phase turns ratio and line turns ratio. I said you the phase turns ratio always constant. Phase turns ratio always constant. X is to 1. There is no change. Always constant. Phase turns ratio is always constant. But the line turns ratio, I am going to find out the line turns ratio. Line turns ratio is equals to line voltage of the primary is to line voltage of the secondary by X. Tell me, what is the line voltage of the primary? We know that in star, line voltage is equals to root 3 times of phase voltage. And this is also star. In this is also line voltage is equals to root 3 times of phase voltage. So line voltage of the primary, line voltage of the secondary. The line voltage of the primary is root 3 times of phase voltage is to line voltage of the secondary is root 3 times of phase voltage upon X. Again, these two gets cancelled out, and again the line turns ratio also X is to 1. Here, therefore, for star-star connection diagram, for star-star connection, phase turns ratio and line turns ratio, phase and line turns ratios are X is to 1 only. Both are same for star-star also. For star-star and for delta-delta, the phase turns ratio and line turns ratio both are same. That too, X is to 1 only. You should remember this point. You should remember this point. Are you okay? Right? It is completed? Right. Now, very important topic here. Very important topic here. In star-star, we have a many disadvantages. Because, see here, the primary winding is star connection and the secondary winding also star connection. There is no delta in our transformer. Nothing but in primary also and in secondary also there is no path for third harmonics, no path for third harmonic currents, no path for third harmonic currents. Here it produces normally EA1 plus EA3 plus and so on. And here also EB1 plus EB3 plus and so on. Here also EC1 plus EC3 plus and so on. These EA1 and EB1, EC1 are nullified from the primary, but these third harmonic currents are not nullified, and there is no third harmonic currents here. There is no third harmonic currents here, and there is no EMF is sinusoidal, or EMF is not sinusoidal. EMF is not sinusoidal. This is the first disadvantage of star-star connection. Because there is no closed path for third harmonics, that's why this EMF is not sinusoidal at all. Not at all sinusoidal, this star-star EMF. And also, generally the fundamentals are rotates with omega angular velocity, but these are rotates with 3 omega angular velocity. The fundamentals are rotates with omega angular velocity, but these third harmonic currents are rotates with 3 times of angular velocity. Now the resultant is 2 times of angular velocity. 2 times of angular velocity. Nothing but here the neutral point is not constant. Here neutral point is shifted from this. Here the neutral point is shifted from this. Here maybe the third harmonic components. The neutral point is shifted from its original position, and this neutral is even not constant. This neutral is rotating with 2 omega velocity. That's why this neutral point is called floating neutral. This neutral point is called floating neutral in star-star connection. This is the major disadvantage. In star-star connection, the neutral point is shifted from time to time, and even it is not constant. This neutral point is rotating with 2 omega velocity, 2 omega velocity, 2 omega angular velocity. That's why this neutral is called floating neutral. This neutral is called floating neutral. This is a big disadvantage of star-star connection. Then, how we can avoid these problems? Here, EMF is not sinusoidal. EMF is not sinusoidal because there is no closed path for third harmonics. And here the neutral point is not constant. This is shifting continuously and rotating with 2 omega velocity. That's why it is called floating neutral. How we can avoid these problems? These problems can be avoided by providing a closed path for third harmonics, a closed path for third harmonics by inserting a delta in between these two windings. By inserting a delta winding in between these two windings, this configuration is called tertiary winding. This configuration is called tertiary winding. Here, tertiary winding. The tertiary winding nothing but, in generally the tertiary winding is used for star-star connection only, not for delta-delta. This tertiary winding is used for star-star connection only. In star-star connection, the delta is connected in between two windings. Due to this, we can provide, due to this delta, we can provide closed path for third harmonics. We can provide closed path for third harmonics. We can provide closed path for third harmonics. Then the EMF is sinusoidal. EMF is sinusoidal because I mu is peaky wave, because the magnetizing current is peaky wave. Then EMF is sinusoidal. EMF is sinusoidal. And this delta gives us a constant neutral point. Constant neutral point. This delta gives us a constant neutral point. And this delta avoids the floating neutral, and it gives a constant neutral point. It avoids the floating neutral and it provides closed path for third harmonics. These are the advantages of tertiary winding. These are the advantages of tertiary winding. Right? What are the advantages of tertiary winding? It provides a closed path for third harmonics. EMF is sinusoidal because I mu is a peaky value, and constant or stable neutral point, and avoids the floating neutral. So this is the advantage of the tertiary winding. Advantages of the tertiary winding. The equivalent circuit of tertiary winding. The equivalent circuit of tertiary winding. The equivalent circuit of tertiary winding. For example, see here. This is my primary. R1X1. This is my primary R1X1. We have only single primary and two secondary windings. We have only single primary and two secondary windings. Let's see here. This is my one of the secondary, which is transferred already. Equivalent circuit. This is equivalent circuit of tertiary winding. Equivalent circuit of tertiary winding. So this is R2 dash and X2 dash combinedly is called as Z2 dash, and here the load voltage which is called V2 dash. Now this is connected to this one, and another secondary also is there, right? Another secondary also is there, right? This is R3 dash and X3 dash, R3 dash and X3 dash, and this is the V3 dash, the load voltage V3 dash, and this is the equivalent circuit of territory winding. Equivalent circuit of territory winding. This is the I2 dash and this is the I3 dash. This is the equivalent circuit of my territory winding. Sir, can you tell me what is R2 dash? R2 dash is equals to R2 by K square. Sir, what is K? The K in between second and first one. The K is in between, K is equals to N2 by N1 or E2 by E1, like that. Sir, for example, what is R3 dash here? R3 dash is equals to R3 by K square. Sir, what is K here? K is equals to N3 by N1. K for third winding and first winding. Nothing but here K31 is equals to N3 by N1 or E3 by E1. Here K21 nothing but as usually E2 by E1 or N2 by N1, like that. Like that you can calculate all the values. This is the equivalent circuit of my territory winding. Here only single primary and two secondary windings. Single primary and two secondary windings. Two secondary windings, and Z3 dash is equals to Z3 dash is equals to Z3 by K square, where K is the K31. Like that you can calculate all the values if they ask you. Are you okay? Are you okay? This is the one of the modification to get the sinusoidal EMF in star-star connection. To get the sinusoidal EMF in star-star connection. For example, if this is difficult, we have another modification also. We have another modification also. You know that modification. You know that modification. Generally, in star-star connection, there is no closed path for third harmonics. There is no closed path for third harmonics. That's why we have to provide a closed path for third harmonics. We have to provide a closed path for third harmonics by neutral grounding. By neutral grounding. In this case also, we can provide path for third harmonics. Path for third harmonics. We can provide path for third harmonics. And here the stable neutral one, stable neutral point, like these advantages are there for neutral grounding star-star. This is also one of the modification. This is about the star-star configuration, star-star connection diagram, star-star connection diagram. So this is simply about the connection diagram of star-star and its advantages and its problems and overcome, how we can overcome those problems. Are you okay? Thank you.